Right, so in this video, I just wanted to remind you of a few things that, or how the MolCalc app essentially works. And then also I wanted to look at your assignment and just give you some general guidance on what you actually need to be doing. So you've now clicked on this video specifically, and then your important thing is you need to go to this website. So in other words, go to MolCalc, which will open a page like this, where you're able to draw 3D conformers of molecules. So if you click and you drag, then you're able to twist this molecule, and then you're able to draw some certain substructures like this, for example. So if you click there, you're able to draw benzene, or want to go back to methane, you can do something like that. You can add your elements, for example, if you want to build a chain, then you can add carbon to anything there. So if you click on an element, then you're going to change that, turn it around. You want to zoom in or out, you can just scroll on your mouse and you can see your structure, right? And you can also do it in 2D if you're more comfortable with that. You can use the stereochemistry to then tell you, right, what it is. I mean, that added a double bond now, but I mean, it's because you're adding an additional bond to it. Yeah, so anyway, but that's essentially the idea. Now you saw there's a bit of vibration that's happening there, so it sort of preempted what I wanted to do. So let's say, for example, we start with our methane, and um, let's just change that back again to that. And oxygen. So whenever you're building something in this app, and let's say we want to make that a double bond, you always have to ensure that whatever you're building, you have to optimize. And that's what this optimize button is for. So that's going to find an energy minima for your structures. And I would just ensure that all your bonds are at the correct angles. And I mean, you expect this bond to be sort of linear. So in other words, to make that this carbon needs to be sp2 hybridized. In other words, it needs to form this kind of, if you look at it, oops, that's not really what I wanted to do, but that's okay. So in other words, if you look at it at this molecule from this angle, then actually all these bonds should sort of align. So it's not completely minimized, but I mean, as you see, as I click this, it's sort of going towards that. So it's fine. I mean, it's really okay. Like you're not going to um, really lose out on anything specific by doing that. Anyway, so that's the general idea. And you can build anything that you want. There's a limit on how many atoms you can put here, but everything that I'm asking you is you're able to build this. Now you've been introduced to this in experiment 3. So in other words, you should be familiar to this. Of course, if you click on an atom, you can drag it. And then once you've put it somewhere, you just need to optimize again. Right. Maybe something else that I didn't do in experiment 3 specifically is, let's say, for example, you want to, of course, okay, it's just easier sometimes to go directly to the methane. Let's say, for example, you want to look at carbon monoxide, and then yeah, sometimes this thing can be difficult, but that's okay. Let's just put the atoms off and then have the bonds. Yep, all right. So for example, I mean, carbon monoxide should look something like that, but then also there should be a negative charge on the carbon, there should be a positive charge on the oxygen, and I mean, if you zoom out or in, you can see there's like these positive and negative charges there. So that's, for example, something that you can keep track of. So if you do want to put anything there, so technically there should be 4 bonds, but anyway, there's things like that you can also do. I don't think there's anything in this practical that might be useful in terms of that. But if you want to add something, because you'll see later on when I speak about the assignment is quite open. So there's not really anything that's limiting you. You can really do what you want. You can look at anything. You can look at deprotonated versions of things or whatever. So, all right. So anyway, let's just go back to methane. So something simple to look at. So once you're happy with whatever you've drawn, then of course you click this calculate properties, and you say indeed. So now you're calculating the properties, and this will be quite quick. Even if you draw something quite extensive, something quite large, then it should be quite quick. And of course, depending on your internet strength, then it should be quite good. So what we have here is some thermodynamics, vibrational theory frequencies, molecular orbitals, and polarity and salvation information. Let's start with the thermodynamics. Zoom in a tad here. So of course, the thermodynamics information, you get some information on your enthalpy, your entropy, heat of formation, and then other things about the heat capacity. You won't really be doing anything about heat capacity in this case or in this assignment. So we'll mainly be focusing on enthalpy and entropy. And of course, when you have enthalpy and entropy, you're able to calculate something like the Gibbs energy. I mean, so delta H minus Ts is going to give you the Gibbs energy. And you can assume you're working at room temperature or whatever. So things like that. So that these things just give you the translational, rotational, and vibrational energy contributions. I mean, if you look back at your second year notes, you'll perhaps remind yourself of something called the equipartition theorem that gives you the contributions of these things. So that's how molecular mechanics models the thermodynamics. And if you do statistical mechanics later on, then these things will also make a lot more sense. All right, so anyway, that's how you can look at this. That's really quickly calculates for you. You can also look at things like the vibrational frequencies, in other words, the IR spectrum. So whatever stretch you're interested in for the molecule, you can look at this IR stretch. So like what you did for the IR, which was kind of cool, I hope, for you. So, but I mean, you're not going to look at it further for this prac. So that is that. And now something that you might not have seen before is, of course, for, so in 385, we looked at molecular orbitals. So if you started to look at molecular orbitals, molecular orbitals are, of course, combined from the atomic orbitals of a substance. So, for example, the lowest molecular orbital of methane looks like the pure s orbital of the carbon. And I mean, that makes sense because the hydrogen orbitals, 1s orbitals, should not be able to bond with the 1s orbital of the carbon. So in other words, this 1s orbital of the carbon is completely non-bonding in terms of the entire molecule. So that's why the lowest energy orbital is so low and is not contributing to any of the bonding orbitals. And as we look here, so this looks like sort of a combination of all the s orbitals of everything. Well, not actually the s orbitals, but some of the p orbital, the p orbitals of the carbon are starting to mix with the s orbitals of the hydrogen to form one of the first bonding orbitals. And you can see they're all in phase. That's why they're all the same color. So that's where we find one that's out of phase. So this one is out of phase. In other words, you see here something is bonding in phase. In other words, you can sort of see a p orbital here if you think about being in phase and out of phase. So one of the ones that are out of phase is bonding on this side with the hydrogen, and the one that is the phase that is in phase with the p orbital is bonding here. Actually, now that I realize it's probably actually all s orbitals here as well, but difficult to, molecular orbitals aren't always easy to assign. But anyway, the ones that I ask you to assign are easy because they're pi orbitals. But anyway, and so you can go through these and try to identify them as well as you would like. The most important one, so for example, like this is almost impossible to classify according to P and S theory, because, I mean, what the hell is that? So anyway, if you look at the most important ones here is your LUMO-HOMO gap. So this is your HOMO, your highest occupied molecular orbital, is the last minus, and the LUMO is your first plus. So here where the minus and the plus are separated. So the LUMO, your lowest unoccupied molecular orbital, tells you where does the electron stop filling, and of course the HOMO is the highest occupied molecular orbital. So in other words, where is the highest molecular orbital where there are still electrons? In other words, if we want to excite an electron, this is the amount of energy that we will need to excite an electron in this molecule. And then you can infer some electronic properties from that, from this for the molecule. Right, so you'll see it has much nicer applications when you look at some conjugated systems, like in the practical or in this assignment. So anyway, so I mean, this is kind of nice. And you can add your pictures. And the most important part is that the idea of this prac is to use the software to look at things and then try to connect it to your theory. So in other words, like I said here, I mean, you can sort of see this as an s orbital, and kind of rationalize this as maybe as an s orbital, even though you might not think there's bonding between the s orbitals, but yeah, um, it is actually very difficult. There's, as I said, allocating bonding orbitals and molecular orbitals is not as easy as it was made out to be in 385. Anyway, all right. The last thing I want to show you is the concept of polarity. So you can actually calculate the polarity. So I mean, methane, you know, is non-polar. Um, so if you want to look at its dipole, you'll see it has no dipole, right? So it's completely non-polar. And you can also see that from the calculation values, or the values that MolCalc calculates for you. So it calculates the polar salvation energy is basically almost zero. So in other words, you won't really have any um, exothermic salvation energy. In other words, if it releases into, so if you put it into a polar solvent, there will be no net release of energy. In other words, it's not an energy favored process or spontaneous process. It is much more, or it actually be a non-spontaneous process. It will be a spontaneous process to put it in a non-polar solvent. So, I mean, that's what you can infer from these values. Right, and I mean, then there's some other information. You can also just turn the molecule translucent, and you can have some nice things. Right, and remember, always you have snipping tool to your disposal. So whatever you want to put in your assignment, you just snip for me, and then you have a nice little image of that. All right. That's essentially it on MolCalc. And you here need to really use all this information combined for every question. Look what you want to calculate. How does that link? It's up to you. This is an open assignment in that sense. There's no set idea, and I'm going to speak about that a little bit more just now. Right, so for your assignment questions, you will see each of these questions are sort of linked as a section in the practical guide, and I allocate certain amount of marks for them. Some of them have a video, of course, like normal, which you can go and watch, where I give you some additional contents. In other words, where I try to explain what the theory is that I've covered. So in other words, sometimes there's some things that you might not be aware of, like for example, how to hybridize p orbitals to get to molecular orbitals. So for example, like combining them all in phase, like what I sort of started speaking about the methane, how to hybridize the atomic orbitals to look at them. You've looked at it in 385, but perhaps not to this extent for such large molecules. So we look at that, for example. But some of them, there's also nothing. So I mean, like for example, this concept of just solubility, you need to be able to rationalize just, I mean, if I ask you, you want to solvate one of these three molecules, which one of these will be most soluble in ethanol? I mean, that's technically a first year question, but then you should be able to answer that, firstly, from a chemical perspective. In other words, what is your pure chemical knowledge? So in other words, your like dissolve like knowledge, but also use the software to calculate something to prove that it is soluble in ethanol. Because the whole point of this exercise is to use the computational strength or use beta MolCalc to help you then prove that this is soluble in ethanol? Or does that actually support our chemical knowledge? So, I mean, you know, you've probably dissolved other alcohols in ethanol before, right? So you know, the alcohol is going to be the most soluble, right? And which one of these is going to be the least soluble? So go rank them. What do you expect? And does that correlate with what you see on beta MolCalc? So that's what I'm interested in seeing, for example. And that's the whole practical, the whole assignment's point, is to teach you how to see what the computational software does versus what your chemical knowledge is. So in other words, you always have to have your general chemical knowledge, so maybe your organic or your analytical, your physical chemical chemistry knowledge, and then you need to link that with what you now have been taught or what you now see with the computational. So you will have a general chemistry argument always, and then a computational argument as well, right? So the general chemistry argument will always count a certain number of marks, but it won't be all the marks, right? That's something I've been seeing in the the few years that I've been teaching the course, people hand in the assignment and then they just give me all the general chemistry arguments and I give them 0 because it says quite clearly at the beginning of the assignment, it says computational chemistry. So I'm not really I'm interested in knowing does your general chemistry knowledge link with the computation, or does the computation predict something completely different from what your general chemistry knowledge predicts? Right. So how does the two match? That's essentially what you're interested in. Or aren't you able to predict anything with your general chemistry knowledge, and are you only able to do something with the computational chemistry? That's essentially what the assignment is about. Right, so you can go through each of these and of course use the mark allocation to know how much you need to provide. So for example, if you need to provide 30 marks for 30 marks, then it means you need to provide some sufficient amount of information. You can't just write maybe half a page of information. It really needs to be a lot, and you need to explain a lot of general chemistry, how you hybridize these orbitals, what do you see computationally, energetically, etc. I give a lot of information in the guide. I give you some explanations on what I expect, a lot of hints, but it's open for you. It's a philosophical point of view or assignment also, in the sense that there's no set memorandum in that everyone will have to have the same answer or the same type of submission to get the same mark. For example, so two people who get 80% will not have the same type of submission. It will be interpreted in terms of what did you provide? What was your argument? What really did you look at? Because you might look at something completely different to what someone else looked at, but it might be still valid. It might be a valid argument. So it's not really that there's a set memo or something specifically that I'm looking at. There's of course a right answer, meaning that there are things that are completely wrong. I mean, there are things that you can't say. For example, you can't say that I don't know. Well, you can't, for example, say that 11 is smaller than 6. So, you can't, for example, say that 11 electron volt is smaller than 6 electron volt. Or you can't misassign the LUMO and the HOMO orbitals. I mean, those are things that are wrong. But if you correctly assign them and your assumptions or your conclusions from those things that you calculate are correct, I'm not going to mark it wrong. I'm going to look at how you interpreted those, what you calculated, and what you saw. So that's what I'm looking for. Right, so I mean, you can go through all of these questions, you can look at the overview of the questions, and I really hope that you enjoy doing that. Some of them are challenge questions. So for example, question 6.5.1 is a challenge question. So there's no additional help, and you must please try and figure it out. As always, like, you need to give the reaction scheme, you need to predict the product, and if you give me anything that is listed here in my guides, and if you screenshot something, I'm going to deduct marks. So if you screenshot something from my practical guide, I'm going to deduct the number of marks that the question counts. So that's what I'm going to do from now on, because people have been screenshotting things in previous years. So that's my new philosophy. Yeah, so that leads me essentially to the final section, or sections. So you need to reference. So in your reference list, you need to remember that you always have your RSC style. So I mean, this is the fourth time that you, or hopefully the fourth time that you've encountered the RSC citation style. And then of course, so this now means that you're not going to get any marks now for it, but there is going to be a 10% penalty if you don't have the RSC reference style. So I hope you really follow that. But also there is a bonus section. So if you have a nice report, in other words, you've put in a lot of effort. You really just put a lot of effort to make it nice, really formatted your document to a high level, and there's a lot of editorial care, and you've adhered to the university's plagiarism guidelines, and you've done a lot of effort to explain what you've done, not just given me some images and left it to me to interpret on what you've done and essentially search for your marks, then you will get the 10 marks. There's also, you can easily earn more than 100% for this assignment. People have in the past earned 115 out of 100 for this assignment because this is an open assignment. It depends on how well you present your arguments. All right. So that's the point of this section as well. You just need to have a nicely formatted document. I'm not looking for anything childish. I'm just looking for something that's nicely formatted. You've seen all my practical guides in the past and whatever. So everything that you've learned over the past 2 years, you need to show now. You're now in your final semester, and this is your final assignment in your final year. And I really want to see how well you've grown as a scientist, how well you've grown as someone in chemistry. So that's what I want to test. And then finally, if for 3 bonus marks, you're welcome to give any feedback on the course. So feedback specifically on the practical course. So if you have feedback on the theoretical course, you're more than welcome to email the course coordinator on that. But feedback on the practical course for this section, please. This is separate to the lecturer evaluation. The lecturer evaluation you still need to do on me, but this is for just the practical course. So something, for example, that you feel you want to elaborate or explain or whatever, just to say to earn the 3 bonus marks, then you can say it here. But you still need to complete the evaluation form as well. Right. This is just a better, well, I've learned that if there's a mark incentive, then people tend to actually do it. Right. Okay, so that's basically the assignment. I hope I've convinced you that you must please not copy anything from my practical guide. And then also that you just need to sit, think, rationalize, and then do something for yourself. Use Beta MolCalc in an interesting way. You can talk to your colleagues, rationalize on how you want to do things, and read the guide. I really guide you well on what I actually expect you to do. So like the what you need to do is really written here. So it's not all stated in the videos or whatever. So you'll be able to pass well with what's given here. But then that additional editorial care and maybe thinking a little bit further than just what the guide says is then going to uplift your mark well above what it needs or what you could possibly get by just doing the bare minimum. It's also one of those things where if you're going to leave it to the last minute, you are not going to do well. All right. Good. And that is it for me. I hope you will enjoy this and that it will be something that you see as one of the most fun parts of 382, especially seeing that it's your last assignment for the course. All right. Good luck.